carefully. It's talking about quantum gravity and observations of quantum gravity in the cosmic microwave background.
Thank you. Thank you for energy to have me I thought it's about potential observation of quantum gravity now. It's more than 80 years since Rosenfeld wrote the first papers on quantum gravity, but still we do not have a final theory that everyone agrees on. And the main reason is the lack of empirical tests. So I will ask the question whether the effects of quantum gravity can be observed in a particular situation in the cosmic microwave background. At the end, I will also only be able to give you some limits, some bounds, also no effect that has been seen, but at least we will have a definite calculation from a definite approach. So my talk consists of the following four parts. I first set the stage. Quantum geometrical dynamics, the most conservative approach to quantum gravity, will give the quantum framework on which discussion is based. I then have to spend some time to discuss the theory that the approximation framework enables me to derive those effects. And the main part is the quantum gravitational corrections. And finally, the discussion of the modification of the CMB, the cosmic microwave background spectrum. Let's start with the historical quote by Schrödinger, because this will have some relevance. So Schrödinger, 1926, when he was on the way to discover, or say to guess, his wave equation, he wrote, and let me give here the English translation, we know today, in fact, that our classical mechanics failed, so that is no dimensions of the past, were very urgent. Perhaps this failure in strict analogy with the failure of geometrical objects, that becomes evident as soon as the obstacles of our choose are no longer great compared with the real finite wavelength. Then it becomes a question of searching for analytical mechanics, and the most obvious way is by elaboration of the Hamiltonian analogy on the lines of analytical optics. So the crucial thing is this Hamiltonian analogy, what he did, he rewrote classical mechanics in Hamilton-Jacobi form, and then he gets the wave equation, and knew there should be such a wave equation from Orn's consideration. There should be wave equations behind it, and from the Hamilton-Jacobi equation, he gets the wave equation. And if you do the same procedure for gravity, then you arrive at the following equations. You do first, okay, this is what Schrödinger did, mechanical Hamiltonian and the Jacobi, which leads to the Schrödinger equation, and the gravitational Hamilton-Jacobi equation, which was derived long ago by Peirce in 1952, leads to the relativity equation. So if you are as conservative as possible, that is, you do not expect breakdown of the superposition principle of the standard linear framework of quantum theory, then what you find is a certain wave equation analogous to Schrödinger's equation is behind Einstein's equation. And so if you assume Einstein's equation to be correct in the single density limit and to have a wave equation behind it, then this is what you get. May not be the, and most certainly is not the final equation of quantum gravity, but to give you the first law to quantum gravity, similarly to the Schrödinger equation, which also is not the fundamental equation of quantum theory, but it is the first entry into quantum theory with a lot of applications. Now we owe the relativity equation of course we owe to two gentlemen, John Wheeler and Bryce Pitt. And the main question that I just answered was quantum gravity immediately Einstein equation the same classical limit. Relativity equation, which I do not write out in its full below, it has a constraint from h on psi equals 0. So h is the total Hamiltonian of both the gravitational field and of all non-gravitational fields. And the classical constraint is h equals 0. If you translate it into the quantum version, it's h on psi equals 0. Constraints of this type also occur in loop quantum gravity. So loop quantum gravity is also a version of what is called the canonical approach to quantum gravity, although in loop quantum gravity h is different of different type, and also the relation with the semi-classical limit is far less clear in the quantum gravity than it is here. because this approach is tailored, such as to start quantitative from the semi-classical limit to quantum gravity. On the other hand, starts on the good quantum level and then has to find gravity. Now you have the problem of time in quantum gravity. What's the problem of time? This is the here. This is a kind of stationary zero energy Schrödinger. There is no external time. Why is there no time? Well, John Wheeler explained it here, the black hole. So relatively phase mechanics in a part, which is vanishing in the quantum scale. The quantum scale only have a probability amplitude on the space of all configurations. But of course, in Newtonian mechanics, you still have an external time t. This is the t that you have in the Schrödinger's equation, but in Einstein's field, there is no external time. So if you just follow this route, then it corresponds to the full space-time. And this just corresponds to psi on space of all spaces. But because there's no additional external time, this is all you have. So only have three-dimensional space on the configuration. So external time has completely disappeared from the formula. It's also good quantum gravity naturally because it's the same approach in spirit, and probably also string theory, although there are some caveats there which for the there. So I depend on the three-dimensional method, which is called NEB of X, and all the non-gravitational disagree. If you look more carefully, the grid equation has an interesting structure. Because there's the structure of what is called a hyperbolic wave equation, like an oscillating string. So it has an indefinite kinetic term, which means that you can distinguish one of these intrinsic variables as a kind of intrinsic time, which is fully constructed from space. And in cosmology, this is more or less the scale factor of size of the three-dimensional space. This property, incidentally, is reserved for many perturbations around models, so still you have the size of the scale factor of the universe as the intrinsic time, so to which you can formulate in an initial value problem, for example. Connected to the problem of time is the problem of Hilbert space. Hilbert space structure in quantum mechanics, as you know, is connected with the probability interpretation, especially with unitarity, which is the persuasion of probability in time t. In time t means with respect to the external Newtonian time t, but of course if you do not have any external time t anymore, then it becomes questionable whether you still need to use this structure. Fortunately, in the approach here, or in our calculations here, we do not have to first solve the problem of time for computer space structure, because we are in a semi-classical approximation. It's not that we have a lot of standard machinery at our disposal. So what is the semi-classical approximation here? It's often called the Oppenheimer type of approach. Well, Oppenheimer is well known in molecular physics because there you can distinguish scales. The scale of the nuclei, they are much more heavy than the electrons, the scale of the electrons. So you can make an expansion scheme in the ratio of the two masses. This you also have here, because for gravity there's one distinguished mass scale, Planck mass, as you know, and as long as in a certain situation this Planck mass is much bigger than other energy scales that you have in your model, then you can apply the Oppenheimer scheme. So again, you see quantum gravity is full of analogies with understood physics, so you can take those analogies, case from molecular physics, to apply them to quantum gravity. Now, the answer made is the following. So this is the full wave function, solution of the grid equation. And you might be puzzled by its notation, but it has turned out to be useful. The notation is the following. So what is here simply written down the dependence on the three-dimensional metric HAB. The gravitational part of this Gerhard, R, and Z symbols that refer to the non-gravitational fields, for which we assume the standard field space structure being posed and the standard formulas. So they write instead of the one get the additional scalar field on the electromagnetic field. It's very general. So when you write it as a small as an amplitude and as an e to the I, this is the Planck mass squared times an s that depends only on a complex at this stage, and a small psi that in addition to the metric depends also on the non-gravitational field, which is indicated by CMB. And then you insert this into the equation which contains explicitly the Planck mass, and you make an expansion with respect to the Planck mass equation. This is what you do. Now if you do that, and I don't go through all the technical details, at highest order you find the following. If you evaluate, well, you find the Hamilton-Jacobi equation as expected for the S, because this is what I told you earlier. If you rewrite Einstein in Hamilton-Jacobi form, the wave equation behind it is particular. So if you do the scheme here, of course you find the Hamilton-Jacobi equation S. So this gives you back like a limit from wave optics to geometric optics back an approximate space time. And then you evaluate this small size of the then available Einstein equation HAB, which corresponds to particulars of the Hamilton-Jacobi equation. Now in mechanics, you just have the well-known relation that momentum P is ds over dq, and P is n times q dot. Then the analogous relation is here that you have HAB dot is given by, well, basically ds or 1 over d with respect to the 3 metric. You have here the lapse and the shift function in general that which gives you freedom to coordinate space time into space and time. So this additional freedom, of course, you have at your disposal and you can make use of it. What you write then is the following. You can define then a time t constructed from space in the following way. A little bit similar to ephemeris time in astronomy, which is old-fashioned astronomy. So you have here the psi AD, you have this derivative is certainly metric, and you have here the classical solution, HAB dot, and the integrate over space is defined the time derivative. And what you get is a functional Schrödinger equation, functional Schrödinger picture for quantized metal fields, essentially non-gravitational field, in your chosen external classical gravitational field, the upshift, whatever. And so you find here again the Schrödinger type equation, but now the function of Schrödinger, which is it's not more Hamilton. In this case. So you have here the I, which appears again in this limit. I mean, the equation is really great. There's no conventional unit. It appears only in the same classical form of time unit. And the OED side is the matter-Hamiltonian side. The matter-Hamiltonian is just the integral of the Hamiltonian density, which is a combination of parts of the order to the space-like hypersurface and parallel to the space-like hypersurface. So if there's a token, obviously, that and the shift functions, then you can construct this. So you are at the level of quantum field theory versus space-time. I mean, this is the first you get back. You get it, of course, in the Schrödinger picture, because we started from the Schrödinger picture. But you can go for some path integral approach and see that the path integral satisfies those equations. So you can be either in the path integral approach or the Schrödinger approach. But this is what you get. Of course, this matter-Hamiltonian depends on the general metric coefficients of your space-time. Because it also is emerging to the WCB time t, because it controls dynamics in this approximation. So this approximation you have again regained your time from the timeless approach. And this is certainly enough because for our approach you just want to get going one step more, calculate the correction in this expansion which goes 1 over Planck mass squared. So this is not a full quantum gravity limit, it's the limit where you have still in a certain time available as an approximate notion, but where you can go now one step beyond quantum in a given space time. So these are the corrections. And more formally, we derived them already some time ago with this thing called the Chania in 1991. And in more detail with Andrei Babinski from Moscow, where we also made a connection to the Feynman diagram language and to the covariant approach, which is now here. So what we find by layers of here, and you have the blunt scale in front, so these terms, of course, unmeasurably small, but of course, you can interpret it differently. Now, the question that the anisotropy spectrum, as long as we have thought about the matter background, contains information about quantum gravity in the standard result about the power spectrum and its approximate scaling value natures obtained at the level of quantum physics in curved space-time. So certainly at the level of quantum gravity. So what happens if you go now one step further? We can calculate the power spectrum at a level where you have one or mass scale corrections. So this is the question. This is what we will solve, and we will discuss the size of those terms, which still will be, too small to be measurable, but they will be much bigger than what you would have in the laboratory from quantum gravity. And it's always given by the ratio of energy scale over one mass squared. And this certainly will be higher here, although still small. Now, mini superspace background was that the space of all three geometries is called superspace. It's called John Wheeler introduced in 1968, and Charles Meissner, he was the first to calculate detailed models where you reduce the infinite many degrees of freedom to finitely many, such as the scale factor of a fundamental universe, and maybe some homogeneous scalar field, and he called it mean superspace. So this is the background on which the perturbations can be introduced, the perturbations that lead to the anisotropies in the cosmic microwave background. Now, so we start with the equation for small fluctuations, and they are sufficient in a flat fundamental universe with scale factor A, or you can also introduce the alpha, and that don't really fine. So the idea is, of course, the inflationary scenario in the early universe from which you can get the power spectrum. So I do not discuss other scenarios. We choose also the simplest potential, which is this one introduced by Linden on the lowest one variant of the starting inflation, which is just a mass squared phi-squared term. You can use also other potentials, but what we use is that the last building is the whole condition is valid. So if you have other situations or other models, then the analysis should be done from scratch again. Now the mini superspace equation here is written in explicit form, so this is rather simple. So you have H naught, psi naught is 0, and the psi naught depends only on 2 degrees of freedom, which is the scale factor, or globalism alpha and phi. And here you see the explicit form. So you have this in term, you see that it can be definited as the structure of a hyperbolic equation. 1 over ground mass squared is d2 over the alpha squared minus d2 over the phi squared, we have this potential term. The following I shall use units where h bar c up to equal to 1. The blunt mass has been redefined for convenience, so it's defined as the square root of pi over g, and it has this numerical value. Also this field definition has been performed. Now, in the following, we assume that this second derivative with respect to the influx is divisible from that potential term. This is the implementation of the classical Slow condition of the quantum field. Of course, this may be violated, and if it's violated, you would have to modify the following calculations. But if it's valid, then it's what is called then all the calculations that follow hold. And I should emphasize that this relation has been used in many applications of quantum cosmology. For example, most of the applications of the non-boundary proposal by Arthur Hawking and not the finally proposal by Blanking, they use this assumption here in order to get an effective one-dimensional equation, which is much simpler to handle than the full two-dimensional hyperbolic equation. Of course, we have now to introduce our homogeneities, because the universe is not homogeneous and isotropic, and without it, perturbations you would not see the anisotropies in the power spectrum. So how this is done? Of course, we want to use the full formalism of KH random perturbations, which we do not do here. We restrict ourselves at perturbations in the inflaton to get the first impression of the size of the effects. But eventually, of course, in more generality, if you go to applications, then we very informed this. So you have phi going to phi of t, which is the background, classically rather than phi, and you perform decomposition into Fourier modes with a wave vector k, and this is the absolute value in the usual form of t phi, some overall k, and these coefficients are all k, so they are the relevant numbers for the calculation. I would say that here we take the x as dimensionless. So the dimension goes into the scale factor, and also this k here is the dimensionless number. So you, at the end, want to go to a physical k, which is dimension 1 over length, you should have to redefine this as scale factors. But at this stage, it's just a number. For example, if the space were closed, then it would just be a discrete number n. So you would imagine also that discrete k is just a sum of all n. Now, how does the real equation look like? Well, this was solved long ago in 1985 by Halliwell and Hawking in a very important paper. So you find that you add students to the space Hamiltonian. The sum of the Hamiltonians of all these modes is the sum of all the k's of these hk's. Because they are small, they do not interact with each other, the modes. They come separately, they only interact with the background. Go to higher orders, of course, non-related in their case, then this approximation breaks down. So you have Hamilton side, which depends on the superspace part, and all the fluctuations, which are infinitely many. And you can write down the explicit form of those because they have small fluctuations. The postmodern Hamiltonians are mainly harmonic oscillator Hamiltonians, although with a frequency that depends on the background, that depends on the scale. So this is what you have here. So you have second derivative, and then you have this potential term. You see gradually in the fluctuations, but of course it contains the k and the scale factor and also the mass of delta. It's again written down for your convenience. So how we solve that? We make the ansatz, of course, because there's a sum of all Hamiltonians, you make a product ansatz that derive a full basis of functional as okay, the superspace part of the product of all psi k's that depend separately on an FK. And with a trivial definition, which is not so important, we find this equation type expressed, which is the starting point then for the von Oppenheimer approximation. You have here the derivative with respect to the background, the scale factor. This h here is the Hubble parameter of inflation because we have used the assumption that the derivative with respect to the phi is much smaller than the potential term. We can replace the n phi term basically by one mass times Hubble parameter, which is roughly constant. And here is the part corresponding to the fluctuations, where again I've written down the expression. So this is the starting point for the von Oppenheimer approximation, so which parallels to the general derivation that I have sketched at the beginning. So again, von Oppenheimer, but now applied to a particular situation. So if we follow the general scheme, we make the ansatz that psi k is written as EIS, and S can be arbitrary complex state, and we expand S in powers of the Planck square. So we write S as Planck square as naught plus m zero's power is 1, and okay, this is how far we go, 1 over Planck square is 2. Again, we insert this ansatz into the full equation, and we compare consecutive orders at Planck square. This is what you do. And we discuss the equations that arise at these consecutive orders. First order tells you that S naught is independent of the SK, it only depends on the background. And the next order is an equation for the background of S naught, which is the Hamiltonian equation. Remember, this is what one progressively has started from anyway, so the formula is necessary there. And the background here is now only the expanding three-point reverse, so it's a simple equation. Very simple equation, and you can solve it explicitly. So this is the solution. It's just e to the 3 alpha times Hubble parameter over 3. Now, then the next order. Remember, in the full approach, the next order you find the functional Schrödinger picture, the functional Schrödinger picture equation, functional Schrödinger equation. And here again, you find then Schrödinger equations for the psi k k, and for this you have to make a conveniently definition. You write the psi k 0, these are the meta states, that is all the zeros, or you extract the prefactor gamma of alpha and write the gamma alpha times the I as 1y, because if you impose a condition on gamma that is the usual condition for the WAB prefactor, then heat waves become simplest. The reason behind it is the following: if you have no matter degrees of freedom, then it's 1 over minus g. It's the same as the WAB scheme for gravity by itself. And of course, there you get the differential equation of prefactor that you find in the WAB. And hence, as in the full case, you can introduce this WAB time, EOET, which is basically nabla of S0 times nabla, which is here, well, for convenience here, the S0 over the alpha, E over the alpha. So from the relativity equation, you find then the bottom line of this order that all the various modes, the various quantum states for the various modes obey this equation, I, E over the Q psi k 0 is H psi k 0. So now we have corrections. So the next order, again, you have to do some formal manipulation. So the next order, you have to be S2. You can write it in a form where you have quantum state one part that depends on your gravity, another part depends on gravity and the mode, and you demand that this data be the standard data formula to be correction. And then you get the wave function sine k1 that has the previous order times dpi 1 mass minus 2 eta, then obey the quantum gravitation corrected for the negative. So you see here, again, it's the next order you have to manipulate all the modes, but then you have your definite expressions 1 over gamma squared, for sine k1. You see here, you have the delta square of this Hamiltonian, which emerges here. This was the potential for Riemann background. You also have this interesting term which violates unitarity because it has explicit I. It's not surprising that such a term is present here because they're no longer at the level of the Schrödinger equation, but at the level of the relativity equation, and they keep on conservation law. It's the conservation law corresponds to the Planck-Gordon time product. But it turns out that in most situations, if you make some estimates, this term is much smaller than this term. So I will only focus on this term and what follows. So how do you solve the equations? First we solve the uncorrected and then we solve the corrected. For the uncorrected, we make a Gaussian ansatz. This is the usual thing that you assume for your inflation, for the base delta ground state at the beginning of the inflation. So they are Gaussian states. You're not forced to do that. You can use other states and do a calculation with other states. But I mean, for definiteness, the Gaussian state. This you insert into the Schrödinger equation, you find differential equations for the reflector and for this omega in the exponent, which you can solve. And so this is the solution, so you can give a solution for this and this, and this is the solution for the omega. So psi is a convenient dimension that's variable means k over h times k. And so this is the main result of this order. Corrections are of the order mass of the inflaton over R squared, but we assume the mass of the inflaton is small, as is usually done. But it will become smaller than the R state. Now we have the power spectrum according to standard formula on inflation theory. So over sheet the density contrast is given by the delta K, which is the density perturbations over the potential of the background, the generation background, and the formalism when inserted tells you this is the phi dot. This is the evolution of the background times this sigma K. Now what's the sigma K? Sigma K is just the expectation value of Fk squared in the quantum state. So it gives you, in a sense, the value of the modes. And by standard expressions, it's just here Gaussian integral, and you get standard results for And then going through formulas as presented in textbook, many textbooks of inflation, then you get here this density contrast at re-entry of the modes. So remember in inflation, you have the parameters approximately constant, so the modes are stretched outside during inflation, and in post-inflation during matter application dominance, they re-enter the Hubble state. So this is what means T-enter here and T-exit. You can relate T-enter to T-exit. Again, these are textbook formulas. So we have the contrast at exit and at entry, and you have this relation. And we define the power spectrum in the following way. So dk of T-enter squared times kq. Then you find this result, which means that the spectrum is approximately scale invariant. Small corrections with logarithms, but basically this is the derivation of the standard result. And so what we shall now do is discuss the modification of it by going one order further in the quantum gravity expansion. So the solution of the correct Schrödinger equation, we assume that you can still do a Gaussian ansatz and implement over Planck mass square corrections in the prefactor and take the exponent. And if you insert this into the correct Schrödinger equation, remember you have 1 over Planck mass squared corrections, then you get an equation for this omega. So that's a differential equation which is written here in homogeneous equation, and this can be solved mostly analytically up to a numerical integration that is involved. And this is the result. So I talk about the solution of the equation. What you find here is that, again, because all the formula we calculate the power spectrum by all this relation, but now with the modified quantum state. And the result is that this unperturbed power spectrum gets here an additional factor, which depends on the scale. This is the explicit form, so these numbers come from the numerical integration of the integrals which you find in solving the equation. So you have this scale dependence. And here when plotted, you see that for large k at this stage is dimensionless here in this approach. So this is why I have just numbers, the approach is small. There are no modifications for large k, which is for smaller and smaller scales. So the larger the scales are in terms of wavelengths, the bigger the effects are. So these are the scales that lead first, the Hubble scale in inflation, so they are the most sensitive to quantum gravity scale. And you see what is decided for the corrections is the ratio of the Hubble scale, which in natural units is a mass squared over Planck mass squared. So this is this. So the effects are more pronounced if the Hubble scale is closer to the Planck scale than it is away from it. Now we know already that it's sort of away from the Planck scale, and that there are already limits on age from other considerations of the ratio of scalar to tensor mode, and that if other constraints are such that age is restricted to be, smaller to the 10 to the 14 GeV, which is already 5 orders of magnitude below the Planck scale. So if you use that number, then you get unobservably small corrections here. Unfortunately, or I should say, for consistency, because the corrections are sizable only if inflation happens close to the Planck scale, because the Planck scale is concept the quantum gravity correction. So what this shows is more or less a kind of principal approach to extract concrete expressions from quantum gravity approaches that really have an effect that is so big that you can see it. So it's not that you just make heuristic arguments that you have to expect by dimensional arguments in that direction, or you have a particular approach for which you can good reason to be a valid approach in the first approximation, and from this you calculate definite numbers. And still, although these terms are too small to be seen, they are much bigger than the corresponding terms in the laboratory situation. For example, if you calculate the quantum gravity correction to Newtonian potential, you also find complete concrete numbers, but in the laboratory, of course, they are suppressed exponentially by 10 to the minus 40 for such number. You know, by the inflation, they are, of course, real. As I said, the effect is most pronounced on large scale. Yeah, the accuracy is limited because they are masked by cosmic variance, but the fact that you only have one universe, and that's all statistics, of course, and it's limited. There will be found definitely a suppression of power at large scale. From non-observation, so far non-observation of this effect, you will find a rather modest bar on that page has to be smaller than this number, which is less constraining than the number we already know. But if you didn't know any constraint before, this is what you get from the non-observation of this. Using the limit set by the W maps satellite. Yeah, as I said, you already have unfortunately stronger limits. So at least we are consistent with what is there. You can try to do this, I mean, what my last or second to last constantly. Also with quantum cosmology, because more or less at the same time that the same journal paper by Koyoba and Suihara, where they calculated the loop quantum cosmology corrections at and without going into the formalism here, which is different from the one Oppenheimer's used, just presenting the result. This is from their paper copied on the power spectrum. They use a certain model of good quantum gravity, which is here the outer curve. And the dotted line is the classical case, and the solid line is what they from the experimental outer bound. So, in contrast to what you find on the relativity equation here, you find an enhancement of power at large scale. So again, these terms are too small to be seen, but at least you can see how different approaches lead to different predictions. And if you approach the Planck scale, you would use this to discriminate between approaches, because they don't do the same result. So in the summary, you can find concrete predictions on a conservative approach to quantum gravity, which is consistent with existing observation limits, but still is small to be seen. There are no additional transplanting effects needed here to understand this, because it's already a quantum gravity theory reference to all Planck scale effects are present. There's nothing to be added by that. As I said, too small to be observable. But basically, one can find this prediction along those lines, which I don't know at the moment. The comparison with other approaches, loop quantum cosmology, different enhancement, large scale, but there are also other approaches, for example, non-cognitive geometry and string star cosmology, and they seem to predict a suppression, like we did, although of course different numbers. So that's it, and I thank you for.
Perhaps I missed it, but did you write down the time evolution of the scale factor in your analysis?
Yes. So it's just we use a flat three-month level background. So the classical evolution basically is the exponential age. First of all.
But the cosmic microwave background is at a stage of cosmology where this scale factor is invalid. It's after inflation. This is true only during the inflation.
Yeah, so the calculations are done during inflation. So the quantum states are used during inflation, but then when you use this result, then via the standard relation of Hubble scale exit to Hubble scale re-entry related density contrast at inflation to the density contrast at the Hubble scale entry at a radiation dominated phase, which was but the calculations are done at inflation. So the corrected Schrödinger equation and the speed equation are applied to inflationary scenario.
So
the data has been so late. In the usual approach, you then relate the unperturbed equation and what happens later. And here we have to resolve this equation that can relate to data, so you have also aspect of data.
I suppose I was asking whether you could see from your approximation the exit from inflation by time involving your Schrödinger wave.
Well, I mean, this is, yeah, this is not seen, you know, not added in the answer data. So of course this would be the full quantum gravity state that we want, because it is not captured by this one. Okay.
You didn't consider the calculation of the K factor, but only the calculation of the matter part. The reason why you call it the quantum gravity.
We have, I mean, elected those sort of visual gravity in the see how strong produces and it seems to us that the gain and the gain and funds arbitrary would not be quantitative changes, all those impressions. But your question is valid, and whether the gain and models lead to enhancement, I don't think so, but it is to check the blockchain form of logic paper, so there's a direct comparison to analysis, but I keep it in mind.
Other questions?
When you consider the continuity in class, you introduce a time function. You define the time function.
It was a classical.
My question is, what is the relation between the time function around the classical time?
So these times, T is the WKB time. That comes in its approach from the highest order of the Oppenheimer. Yeah, so the T is not there at the beginning. It's defined, well, yeah, I can see it somewhere here. Yeah, so this is actually the T. The T that you see is always the same. And it's the T that you so it's in the T, you see that you have the state, which is timeless, and E which is timeless, and the is constant, the highest order. And the highest order you find here, they have a Hamilton equation. And if you have that, then you can find a closed solution of the Hamilton equation. You have this combination. And it's defined, and it's equivalent to the classical Friedman the left time. The proper consistency. So the time that you have the classical equation is, of course, to get back at WK time in quantum. But of course, in general quantum theory, you have many solutions that do not specifically say that so there is not. It's only the state of that form that you have in that form that molecule is moved to the state you can define time. So outside, I think that the regime, I think that's the part.
Other questions? Thank you very much.